I've just finished writing this contest. As you can see, it's still going. And I want to share with you my solution for problem D. We'll solve both easy and hard version. But let's start with easy. So you can read the statement now, or in my words, the statement is as follows. We have a sequence of numbers. Lost my cursor. We have a sequence of numbers. Yeah, suppose those are numbers. We want to break it into two sequences, saving the order. So some of the numbers will go into one sequence, some will go into the other sequence. And then for every value, for every number, we pay a specific price. But if it comes after the same value, then the price is lower. So for each value, we pay such price by default. But if it comes after the same value in this sequence, then we pay a lower price, which is also defined for each value. And obviously the question is to break the sequence in two, minimizing the total price for each value. We'll use a method called process_dp. You can read about it in details in my blog. But in short, it's applied when the problem asks about some objects, about some specific objects of some type. Like in this case, an object is a way to break the sequence. Let's call every such breaking an object of the problem. When you want to calculate the number of such objects, or to find the object which has the minimal price, yeah, like in this case, you can use process_dp. In short, in order to use process_dp, this method, you must construct or think of a process that will build such objects step by step. In this case, the simplest process that we can come up with is just scan through this sequence and step by step determine the fate of every object, yeah, one by one, if it goes into the first sequence or to the second sequence. So on every step of our process, we just consider the next and the next and the next object, and either add it to the end of the first sequence or to the end of the second sequence. We have to remember some information about the previous actions that we made, about the previous choices that we made. This information will be stored as a parameter of our DP. So in this case, what information do we need to store? Obviously, first parameter is we need to remember how far we went, yeah. So how many objects we already considered. Let's call this parameter I. It's how many objects are already considered. This is sequence 1, this is sequence 2. This is our original sequence. First parameter is how many objects we already considered. Then, on our next step, we will either append this value to the first sequence or to the second sequence. Of course, we need to know the price. We need to know, will we pay the full price for this value or the decreased price, yeah, the smaller price, called hot here. So in order to know that, we need to know what was the last value added to the corresponding sequence. So the most naive way to do it would be just to store two additional parameters. what was the last value added to the first sequence so far, and the last value added to the second sequence so far. So to this point in time, this was the last value we've added to the first sequence, this was the last value we've added to the second sequence. So we could have three parameters: I, last one, last two. And those are values added to the first and the second sequence. The last values added to the first and the second sequence. But obviously, one of those two values will be I minus 1, yeah? Value with index I minus 1 will be one of those two. So it would be kind of excessive to store both of them. We can just store which one of them is I minus 1, which one of them is the value at position I minus 1. And for the other, we store its value. So for example, in this case, what can we store is the last move, yeah? So where did we add the previous value? In this case, it will be 2, yeah? And for the other sequence, for the first sequence, we store this value, the last value added to this sequence. So our DP has three parameters. How many values did we consider so far? How many first values? What was the last move? Let's call it last move. So let's say it's 0 or 1, yeah? It's 0 if we added the last value was added to sequence 1, and it's 1 if the last value was added to sequence 2. And the last parameter will be j. It's the last value added to the opposite sequence. So in this case, this will be number j. This number is j. So we store the number that was added last to the opposite sequence. The opposite to that. And from here we have two transitions. We can either add the new value to the same sequence as the previous, as on the previous step, or to the opposite sequence. And that's basically it, because this is already an n-squared solution, to be precise, nk solution, because this parameter is up to n, this parameter is just two values, and this parameter has k values, all of k values. So there are two nk states. From each state we can do just two transitions. So the overall number of transitions is nk, O of nk. If you implement it correctly, it will pass the easy version. Let's look how I implemented this version. Okay. Read the sequence, then these are the full prices, these are the decreased prices for each value. For each value from 0 to k minus 1. I've also shifted all the values so they are from 0 to k minus 1. I also have an additional auxiliary value k. It's like a non-existing value. It's just some value which did not appear in those n numbers. So I work with k plus 1 different values. K original values and plus 1 auxiliary, which I added on purpose. It's some value which did not appear among those. In my case, it's k, because they're from 0 to k minus 1. Okay. And dp, my first parameter is hidden. Parameter I is hidden. It means that it exists, but I only store the current layer of dp for I equals 0 initially. Initially, I store only states of dp where I is equal to 0. After the first iteration, I will store values of dp only when I is equal to 1. So I does not appear in my table. It's kind of intended I mean, it exists, yeah, but it has a specific value at every moment in time. All the states that I store, they have a specific I currently. Initially, I is 0. So I store the zeroth layer by I, zeroth layer by I. Second parameter, last move, 2 values. And third parameter, including the hidden parameter, of course. The third parameter is the last value added to the opposite sequence, opposite to the last move. This value is after chain inclusively because I added this auxiliary non-existing value. And the starting point of our process is when we consider it 0. Okay, the first hidden parameter is 0 because it's how many we consider. Yeah, the last move. Let's suppose that the last move was 0. Yeah, we've added some value, some non-existing value to the first sequence. And this non-existing value was k, yeah, and the last value added to the opposite sequence is also k. Yeah, so k is kind of this auxiliary non-existing value. Yeah? It just means that we didn't add anything there to the opposite sequence. Then we consider, with each I, we want to shift from layer I to layer I plus 1. So we create a table new DP for layer I plus 1. So new DP are the states where the first parameter is equal to I plus 1 when we already considered the new ith element. Fix the current state of DP, all possible M, all LM, all possible J. So we are currently at DP I is hidden, LMJ. First move that we can make is to add our value into the same sequence as on the previous step, to this sequence. Then we will transit into the state with the same, last move is the same, yeah, next layer, so now I plus 1 values are considered. Last move is the same as before. Last value added to the opposite sequence is the same as before. And the price will be, the price of such move is if the previous value exists, so it means that, so this move means that we will add this value to the same sequence as the previous value. So if the previous value exists and it's the same as ours, so if it exists and they are the same, then we pay a smaller price. Otherwise, we pay a full price for this value. Then the second case, the second move that we can make is to add it to the opposite sequence. So add it here. In this case, I will transit into the state last move is the opposite to the previous last move. And the last value added to this sequence now this is the opposite sequence, so the last value added here is either I minus first, the value on position I minus 1, if it exists. But if it does not exist, then just k. So if I is 0, the last value is considered to be k, non-existing value, because no values were added so far to this sequence. Otherwise, I say that this is the last value added here to the opposite sequence. So that's where I transit to. And the price of such move, I just compare value j, this value, to the new value, this value. If those are one and the same, then the price will be lower. If they're different, then the price will be higher. That's it. And then when I finished counting the new layer, I just shift to the new layer. So now I will be I plus 1. I will move to I plus 1, and the layer that I store is the next layer. In the end, I store the layer n. So when n values are considered, all values are considered. So all values are considered, I've broken them into two sequences. I see and all the possible states on this layer are valid ending states. So I just consider every such state, choose the one which has the best score, and output it. This is accepted. Okay, I'm not sure, but at least it passed the pretest. We'll wait for the system test. Now, let's discuss the hardware version. The hardware version is exactly the same, but now the constraints are just much bigger. So we want to make a solution faster than n squared, or nk in our case. Yeah, our solution works in O of nk, as you can see here, up to n, up to k. We want to make it much faster. One notorious optimization for such process DP, it's like very widespread. When you have a process which does something with every element, yeah, it considers every element or every position, so it moves through positions always by one. Such process is very often can be very often optimized by changing the process. I mean, such DP can be optimized by changing the process. Instead of moving by one position every time, let's jump to the next interesting position. This is kind of vague, but it's on purpose because I want you to be able to use it in many different situations. In many different situations, we can change the process if it moves through positions one by one. We can change it so that it moves by several positions in one step. Yeah. In our case, it's actually quite obvious how to do this. So if this is our sequence, suppose we've came here. So how can we jump to the next interesting position? Next interesting position will be like, okay, we suppose we added this to sequence 1, this to sequence 2, this to sequence 1. Let's say that when we jump, we add everything over what we jumped into the opposite sequence to the last move. So we jump by blocks. When we jump over a block of numbers, we add it to a new sequence, the opposite sequence, every time alternating between sequences. This is like a very intuitive way to change the process. So we will do such jumps between positions. And such jumps will correspond to such answer. We can always start with sequence 1, it doesn't matter. So, how can we now make it work faster? Because if you keep all the same parameters, it will not be faster, yeah? Because you will still have a parameter what value was added to the opposite sequence last. Want to get rid of this parameter. To get rid of this parameter, want to count the answer in a different way. To present the answer in a different way. we need to define the price of a jump. You see we do jumps. Instead of the price for every element, let's define the price for a jump. So when we do a jump, let me draw it once again. Let's draw a large jump. All of those values, we know what price we'll have to pay for them. It's only not obvious which price we pay for this. If the previous jump was like this, for example, then the price for this value is determined by this value. If it's equal, we'll pay a smaller price. If it's not equal, we'll pay a larger price. But for all those values, their price is determined by the previous value. So maybe let's say that every value, or rather every element of our array, has a default price. By default, we'll just put everything into one sequence. And every element of our array will have a lower price if it comes after the same value, or a higher price if it comes after a different value. The first will have a higher price because it does not have a previous value. So let's call it a default price. And now let's once again consider some process. So it jumped like this. Let's see how the price that we'll pay differs from the default price. So for every first element on the block, on every block, except for the first block. For the first block, we'll pay the full price in both cases. For the first element of the first block, we'll, in all cases, pay the full price. But for every first element of the block of the other block, we can pay a different price from the default price. Let me draw it better. The price of this element is determined by if it's equal to this element or not, which is fully determined by this jump. Yeah. So maybe let's attribute the price that we pay for this element to this jump. So let's say then that when we make a jump, the price of a jump is equal to, if it's jump from I to j, yeah? Or let's say from j to I, The price of this jump is negative the default of I is this. So we subtract the default price and instead add the real price. And the real price is determined by if AI is equal to A of j minus 1, then we pay a lower price, which in my code I call y of AI. Otherwise we pay a higher price, which I call in my code x of AI. Minus default. So instead of default price, we pay this price. So for every jump, except for the last jump, we pay such price. For the first price, for the first jump, we also pay this price, but we consider that this value is non-existent, so it's not equal. Yeah, so it's not equal. If j minus 1 does not exist, then we pay full price, obviously. Now, let's just try and write the formula for dpi, where dpi is just the best way to jump into the position I from the very first position, from the position 0. So the best price of jumps to jump into position I from position 0. This is dpi. And we can very easily write out a formula for dpi. You see, we have two cases here. We either pay y or we pay x. Let's consider both cases separately. Let's say this is I. We will subtract the default price, because this is what we have to do in any case if we jump into I. But then let's first consider a case when we pay the full price eventually for this element. Then it doesn't matter where we come from. We can come from any j. It doesn't matter. In some cases, we'll pay even better price. So in some cases, we do not check. Yeah, we do not check. We just allow to jump from any j. In some cases, those elements indeed will be equal, but we don't care. We at least want to cover all the cases when they are not equal. If we cover also some other cases, it's not a problem. But all the cases when those two elements are not equal will be covered if you just allow to jump from any j and to pay price of x in such case. So one way to, so dpi is negative default of ai, default of I, plus, and then the best of two options. So one option is to jump just from any j, smaller than I, of course. So jump from any j and plus pay full price x of ai for this element I. And this mean dp minimal j, so minimal j less than I. So we just need to know the best j that we calculated so far, the best j that occurred before I. Obviously, we can just keep track of the best dp so far. There is no problem in it. And the second case, the second option, is if we want to pay the low price. Then we will have to jump from any position such that a of j minus 1 is equal to ai, so that this element here is equal to our element. So if you want me to write it, this is minimal dpj for all j's smaller than I, such that previous element to j, aj minus 1, is equal to ai. Among all such j's, we want to find just the best dpj, and in this case we pay the price y for this element, for this value. Let's also put it into brackets. So to calculate this, we just need to know the best dp of j for all j's where aj minus 1 is equal to some value. So let's just keep it for every possible value. For every possible value of AI, let's keep the best dpj that already occurred such that aj minus 1 is equal to AI. Or is equal to just some x. We'll call it best from x. So the best jump we can do from such specific value of x. And by from, I mean that it must be previous to rj, so on position j minus 1. Best from will be just this minimum dp for such x, for ai equal to x. Minimum dp of j, where aj minus 1 is equal to x. And obviously, we can also easily keep track of this. So we need to keep track of just minimum dp that occurred so far. So when we calculate dp of I, we update minimum dp that occurred so far. And when we calculate dp of I, we also update best from for ai minus 1. This solution works in O of n plus k. And let's see how it's implemented. Very short code. So read transform every value, so it's from 0 to k minus 1. I add an auxiliary value of k to the very end, so that I don't have to consider a separate case when I make a separate when I make the last jump. It's not a separate case, because here I just put the value k, which is not equal to anything, but the price of it is 0. So I set the price of k to 0. Both low price and high price is 0. So I add this auxiliary value k to the very end. Then I read the prices for all values. For k it's 0. Default answer. Default answer is for every element from 0 to n. If there exists a previous element and it's equal to our element, we pay the low price for this element. Otherwise, we pay the high price for this element. Default answer is when we put everything into one sequence. Then dp of n plus 1 is the best price of jumps, the best total price of jumps to arrive into position I. Initially, it's infinity because we don't know anything about any jump. We don't know any paths of the process. So the best we know for every position is infinity, except for 0. For 0, we know that it's the starting point, so we can start from there and pay 0. Now, minimum dp is, as I said, the best dp that just occurred so far. It's already 0 because dp0 already occurred, so we can always jump from 0, and the price of such jump will be 0. And best from, for every value, initially it's infinity because we don't know best from for any value. Yeah, dp0 does not have a previous value. Value minus 1, value on position minus 1 does not exist, so we don't need to update best from with anything. We don't need to update best from with dp0. Now, for every position starting from 1 and 2 and inclusively, just use this formula. dp of I is equal to, like here I just say that if AI is not equal to the previous value, then I don't change its price. Otherwise, I change its price from low to high. And then, so I just break this bond. Yeah, if those two were equal, I just break this bond and instead pay high price for this. But I may start paying low price again if I decide to make a good jump. So if those two elements are connected, will be connected or will be the same. Yeah, so instead of subtracting the default price, in my code it's a little bit different. Yeah, instead of subtracting default price, I subtract default price minus lower price, so minus y. It doesn't matter, you can write it as I described, but I wrote it a little bit differently. So I kind of start paying the full price for this element, but then I either just make the best possible jump without claiming that this jump will be good. Yeah, we call a jump good if those two values are the same. So if we do not claim that the jump will be good, then we just don't we just pay the full price for this and just see what's the best way, where can we jump from the best way possible. Otherwise, we claim that we want this jump to be good, so we want this value to be equal to our value. So we again start paying not the full price. So we change the price back to y, and we see what's the best jump, what's the best DP, yeah, such that previous value was equal to this, to AI. When we calculate DPI, we update just minimum DP with the DP of I. Rex is this. Just update value, basically. And we update best from AI minus 1, so best jump from such value with also DPI. In the end, we pay default answer plus the best total price of jumps to arrive at position DPN. And as we see, the system test is finished and all the code is accepted. So that's it for today. If you want to know about this process DP in more details, you can first of all read my blog and subscribe to my channel, because I will make more videos about it. Also, I remind you that I give private lessons in competitive programming. If you're interested, contact me via Telegram. Goodbye.